Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at section 4.9, and this is finally when we're going to get into integrals for this course. So we first define them as antiderivatives. So a function f is an antiderivative of little f on the interval I, provided that the derivative of big F with respect to x is equal to little f for all x in I. So let's see what that means. Let's say I have a big F here equal to 2 sine of x, 2 sine of x, and I have a little f here equal to 2 cosine of x. Alright, and let's say I'm trying to find an antiderivative for 2 cosine of x. Well, we know how to find the derivative of it. The derivative of cosine is negative sine. So the answer for the derivative of this would be negative 2 sine of x. But we're not asking for the derivative of this. We're asking for the antiderivative of this. So one way to look at it is, well, if I take the derivative of this function here, 2 sine of x, I will get 2 cosine x. So that means that 2 cosine x, or that 2 sine x, is an antiderivative of 2 cosine x, because when you take the derivative of the big F function, you're going to get the little f function. All right, let's kind of get some of these. So let f be any antiderivative of f on an interval I, then all antiderivatives of f on I have the same form, f plus c, where c is a constant, an arbitrary constant. And that means that for this function here, it doesn't matter if I add 2, or if I add pi, or if I subtract something. When I take the derivative of this, the constant is going to fall off, right? So that means that all of these functions here, where I'm adding any kind of constant, are still antiderivatives of this function here, which means that if I was just given this function here, f is equal to 2 cosine of x, if I was just given that function right there, probably should write f of x, that, and I found the antiderivative, well, that would be the antiderivative. So big F would be 2 sine of x. And since we don't know if there was any constant added or subtracted from the original equation there, we just have to do plus c. And plus c allows for any arbitrary constant that may have been in the original equation here. So we don't have to do that for derivatives, but we do have to add that c for antiderivatives, integrals. All right, and we're given the first rule here. Now, this symbol here, this is an indefinite integral, and it's basically telling you to take the antiderivative. Take the antiderivative. So let's go ahead and do an example of that. All right, so suppose we have the function g of x is equal to 11x to the 10th, and we want to find the antiderivative. In fact, we want to find the entire family of antiderivatives. And we want to use the indefinite integral. That's just a way to find the antiderivative there. So if you want to go ahead and give it a try using this rule right here, go ahead and then I'll walk through the solution. Alright, so the way we set it up here is like this. We do our indefinite integral, and indefinite integral means this. It means that there's no limits here on the bottom and the top of this. If we do have limits, limits of integration, then that means that we have what's called a definite integral, not indefinite. So indefinite means we just put the little squiggly thing. That was a horrible squiggly thing. Let me try it one more time. Just something like this. And then we're going to put the function in here, 11x to the 10th power. And then we always put a d, well, whatever variable we're taking the derivative with respect to. So in this case, it's to x, so we put a dx. If we were taking it with respect, the antiderivative with respect to z, we put a dz there. And it's important because sometimes we'll have more than one variable in a integral. Not so much in this class, but if you take Cal 2 and Cal 3, you'll see that more often there. And then for this one, basically what we're going to do, and I'm actually going to jump down just because I think it's a good introduction to this next rule, the constant, multiple, and sum rules. But I can pull any constant being multiplied by the function out of the indefinite integral here. So this is going to become 11 x to the 10th dx. And this makes it easier, and I pretty much do it every time when I'm doing integration here. And now the rule says that we're going to add 1 to the exponent and then divide by that same number. And then we're going to add c. So once we apply the antiderivative rule, we drop the indefinite integral symbol. So this is going to be 11, and then this is going to be times x to the 11th all over 11 plus c. Don't forget the plus c once you actually take that antiderivative. Here the 11s will cancel out, and I'm just left with x to the 11th plus c. So that means that, what does that mean? It means that any function in the form of x to the 11th plus a constant, so x to the 11th plus e, x to the 11th plus 100, x to the 11th minus 1,000. If I take the derivative of any of those functions, I get my original one back. Can't you see that? You just pull the 11 out front, subtract it by 110. So if you take the derivative, you get 11x to the 10th, which is this. And the c will cancel out because we know when we take the derivative of a constant, it becomes 0. So this is the family of antiderivatives that satisfies this right here. All right. The sum rule just says that basically you can split them up into separate intervals if you're adding or subtracting, very similar to regular derivatives. And next I'm going to pull up just a bunch of the antiderivative rules. Okay, so here, and these are, let's see, we have some on page 327 with some examples, and we have some on page 325 with examples. It shows the derivative on the left, and then it shows the antiderivative on the right. So since the derivative of sine of x is equal to cosine of x, then the antiderivative of cosine of x, dx, is equal to sine of x plus c, and so on and so forth. So you kind of have to kind of do the opposite of what you were doing with when you were taking the cosine, or the derivative of the cosine and the derivative of the sine. Now with the antiderivatives, the minus sign goes onto the other one. All right, let's take a look at another example of finding the antiderivative of a function. Okay, here I have the integral of secant squared of x minus 1 dx. So first thing I'm going to do is I'm going to use that sum rule in here just to kind of break this up into two different functions. So I'm going to have the antiderivative of secant squared of x, secant squared of x. Don't forget to put the little dx. You always need those at the end of the integrals there, both definite and indefinite. And then we're going to do minus, minus 1 dx. All right. Once I do that, I go over here and I notice that since the derivative of the tangent of x is secant squared of x, the antiderivative of secant squared of x dx is tangent of x plus c. So this over here is going to be tangent of x plus c. And we have a minus. And then for the 1 there, I'm going to kind of show you one way to look at that. You can look at that also as 1x raised to the 0. And when you apply the rule, that becomes, you add 1 to the exponent there, so that's going to be 1 x to the 1 divided by 1, which is just equal to 1 divided by 1, which is just equal to x. So the antiderivative of 1, remember x to the 0 is equal to 1, so this is still just 1. So the antiderivative of 1 is x. So the antiderivative of 5 would be 5x. The antiderivative of negative pi would be negative pi x, and so on. Alright, so that is equal to minus x plus c. Well, it doesn't actually have to be the same number here, so let's use a different constant. So we're going to have tangent of x plus c minus x plus d. Now, one thing that we do, and it often confuses students, is that we're not going to put plus c plus d in our answer, because what is a constant plus another constant? It's still going to be a constant, right? Or even a constant minus a constant still gives us a constant. So unless we're trying to solve for the actual constants, which we are not in this case, we can combine c and d into just one constant. So this would end up being the tangent of x minus x plus c. And that would be your final answer there. All right, let's go ahead and take a look at one more here. All right, so here's a doozy. We want to find the antiderivative of the cosecant cubed of x plus 1 over the cosecant of x dx. All right, so how do we do this? Go ahead and pause the video, give it a try. I'll give you a hint. Break up the fraction, and when you're ready, turn it back on, and we'll go through the solution. All right, so remember, if just kind of put this up here, if I have a over b plus c over b with the same denominator, that's equal to a plus c over b, right? You just add the tops, put it over the bottom. Hopefully we should know that. So the same is true in the reverse. So if I have the sum or difference of two quantities on the top over a single denominator, I can break it up into two fractions like this. So that's what I'm going to do here. So this is going to be, and I'm also going to use the sum rule to break it up. So it's going to be the cosecant cubed of x over cosecant of x, cosecant of x dx, plus, remember sum rule to break that up into two, 1 over cosecant of x dx. So let's kind of simplify that a little bit. One of those will come out. So we have cosecant squared of x dx plus, and over here, well, 1 over cosecant, let's look at what that is. Let me see, that's going to be 1 over, remember, cosecant is defined as 1 over sine of x. So when we multiply by the reciprocal of the denominator, this whole thing is just going to equal to the sine of x. So 1 over cosecant of x is just equal to sine of x dx. All right. Well, looking over here, the antiderivative of cosecant squared of x is negative cotangent of x plus c. And then the antiderivative of sine of x is negative cosine of x. So this is going to be negative cosine of x plus some other constant. And then when we are finished, this should just end up being negative cotangent of x minus cosine of x. And remember, we have two constants, and I'm just going to combine it under one, calling it c. That's because we're not trying to solve for the constants. And that is your answer. All right, guys. I hope this helped. Please try some of these, some more of these in the book and in the homework, and let me know if you have any questions. Thanks.